Welcome to the first video in a course on calculus. In this course, I plan to deliver the material you'd see in a usual undergraduate calculus course. And since the material is huge, I figured that there should be some slides to refer to as a reference. Rather than having to write everything down, I'll be just writing the explanations of things. So this first video is about sequences and limits. So we're gonna start by defining what sequences are, and we're gonna discuss a few tricks to calculate a few tricks and rules to calculate limits of sequences. And I want you to take these videos as a place for revision, where you'd find everything condensed in one place. So what are sequences? So let us give a rough idea first of all, and then we do the rigorous mathematical definitions. So a sequence is actually it's a collection of objects. So it's a collection of objects, and you can say it's a list of objects where repetition is allowed and order matters. So what do I mean by that? So for example, if you consider this sequence formed of the letter G-O-H-N, John, and this is a sequence of these letters. In fact, it's a list of these letters, right? And usually, if you're a computer scientist, you've seen that such a list is indexed, right? So this is of index 1, this is of index 2, this is of index 3, and this is of index 4, right? So repetition is allowed. So for example, you can take a list where you take two n's, for example, at the end. Repetition is allowed, and there is no problem with that. The typical way of writing a sequence is by not writing these things, because the sequence can be infinite, right? So you don't write the brackets, the square brackets. And so for example, one way to represent a sequence is by listing its elements as such. So you have this list, and so repetition is allowed, and order matters in the sense that you can't just permute two elements of this sequence and remain, like, you can't just get the same sequence. Like for example, if you permute the O and the J, this is a different sequence, right? So the order matters in this sequence. And so let me just give you a more intuitive idea of why order matters here. So if you take, for example, the sequence 1, 2, 3, 4, and so on, so it's an infinite sequence. And so for example, this sequence, there's another way of writing it. So typically sequences are written as, you take a letter, usually A or B, and you index it by n. And for example, the above sequence can be written as an equals to n, meaning this is a1, right? This is a2, this is a3, for example, right? And so on. So so you see the index in this case is equal to the element of the sequence, right? So if you permute, for example, 2 and 1, right, and you leave the rest the same, for example, like this is no longer the sequence an equals to n, because a1 is 2, right, and it's not equal to 1, right? a2 is 1. What is a2? What is this thing, right? It's the element, the element at index 2, right? a2 is 1, which is not equal to 2, right? So the order in a sequence matters, right? So this is the definition of a sequence. Let me just restate that. A sequence, it's a list of numbers. In fact, it can be a list of anything, but we're interested in list of numbers. So it's a list of numbers in a given order. The order matters. For example, you can take the list of even numbers, like the 2, 4, 6, 8, and so on. For example, this sequence is an equals to 2n, right? So there are two ways of writing sequences. You can write it in a compact form as such, or you can list the elements of it as we did here. So so again, the index of an element, the index, right? The index of an element is its position in the sequence. So for example, what's the index of 2? It's 1 because it's in position 1. What's the index of 8? It's 4 because it's in position 4. And again, so the index is going to appear as a sub-letter, as a sub-number of a letter A or B, usually talking about sequences. So for example, A1 here is 2, A2 is 4, and so on and so forth. So a general term in the sequence is 2n. So if you have a list of numbers, if you have a sequence of numbers, how do you write it in a compact form? You will need to figure out what's the general form, like what's the element at a general index, what's the element at what's the element at position n. How can you write it as a function of n? And once you do that, you get a compact form of the sequence. There is another way. So these are kind of multiple definitions of what a sequence is. So there is another way of defining what a sequence is, and so here's another way. So you can define it as a function from the natural numbers to let me just say the list given by the sequence, right? And in fact, you can just say R to R or to C, but in this case, what are the natural numbers? These are just 1, 2, 3, and so on. And what are these, or what is R? Well, R is the set of real numbers, right? And what is the list? For example, you can just consider it as a function from n, the natural numbers, to the list of numbers. For example, if you consider this sequence, the list is like 2, 4, 6, 8, 10, and so on. So this is the sequence that we're talking about, and you can consider the function more generally as a function that is real valued, meaning its image is an R. So why is every sequence a kind of a function that is defined on the natural numbers? Well, it's because you can define f of n, so f at a natural number, to be a sub n. So it's kind of a function that you give it an index and it gives you the value at that index. It gives you the value at that position, right? So this is what a sequence is. And we're gonna take now some examples. We're gonna define convergence and divergence, and we're gonna start talking about limits. So here's the first definition in our course, or mainly the second definition. So what does it mean for a sequence to converge, right? So let me just give you a rough idea here. So let's consider the sequence an given by 1 over n. Another way to write this is like at position 1 you have 1, at position 2 you have 1 over 2, you're plugging n here for different positions, then 1 over 3, and so on. So you have this sequence, and if you look at this, every time like you look at a number at a bigger index, you will see that you're dividing by a bigger number, right? So intuitively, you would think that since we're dividing by big numbers as we go, this is going to it's going to 0, right? Because it's going to be 1 over a huge number. So it's kind of going to 0. And we need to make the idea of going to zero more rigorous or more mathematical. So the way to do that is we define what's so-called convergence. So we say a sequence is convergent. So let's call it a sequence AN, for example. It is convergent to a limit. So this is called the limit, right? So in this case, this is the sequence and this is called the limit, right? So a sequence AN is set to converge to a limit L if for every epsilon positive there exists a natural number n such that this happens. So I'm going to explain what's happening here, but before I do that, let me just tell you that this definition is beyond this course, but we're gonna need it, and it's usually covered in undergraduate calculus courses, just for the purpose of proving, for example, why 1 over n would go to 0, and then we would develop on this using other tools. So this is only needed for the first lecture, I believe, and it won't be needed much, just to prove a simple thing. So let me just tell you the idea. So what does it mean? What does this definition means? It means that if you choose an n big enough, that is big enough, and you look at indices that are bigger than that n, then a n will be close to L, and it will be close enough, right? By epsilon here we mean a very small number, so this is a tiny number, right? You can think of this as a tiny number, and you can think of this as a big number, right? And by this definition, what we mean is that we want, or we say that the sequence converges to L or has a limit L if eventually, if we choose a big index, we're gonna be epsilon close to L. So AN is gonna be like in a distance less than epsilon from L, right? So we're gonna use this definition to prove that, for example, this sequence converges to 0. Because intuitively it is true, like you can think of it as like the numbers are getting 1 over huge, then it should go to 0, but we need to prove this mathematically. And we won't need this definition for more than that, I believe. So before we do that, let me just tell you another notion. So the opposite of convergence is what's so-called divergence. And a sequence is set to diverge, right? A sequence is said to be divergent, or is called divergent if it's not convergent, if it doesn't converge. So what does that mean? For example, let's consider the sequence an equals to -1 to the n, right? So what is this sequence? Let's write a few terms of this sequence. So for n equals 1, this is -1, right? -1 to the power 1. For n equals 2, this is -1 squared, and it becomes +1. And then we have at index 3, we have -1 cubed. But what is -1 cubed? Well, -1 cubed is just -1, and so on, right? You will see that this sequence is alternating, +1, -1, +1, -1, and so on. So if I ask you to tell me what will happen eventually to this sequence, you just have no idea, I mean, right? So you just have no idea where this sequence is gonna be, is ending up, right? So this is what's so-called divergence, because in this case the limit does not exist. So there is a way of defining rigorously what divergence means, namely you negate this statement, but we're not going to be needing that in this course. So let me just tell you a little bit more about what a divergent sequence means. So a divergent sequence is a sequence that's not convergent. And when does a sequence not converge? Like, when does it not converge? Like, a sequence doesn't converge when its limit, and we're gonna make this more rigorous, when its limit, right? If you send the n to infinity, if you consider the sequence and send the n to infinity, and you're trying to tell what's happening for big N. So if you do that, if you take the limit, you either get infinity, or you get that the limit does not exist. So for example, for the case of an equals to -1 to the n, if I ask you what happens as n tends to infinity, you tell me I don't know, because it can be +1 or it can be -1, right? So in this case, we say that the limit does not exist. So for this reason, since the limit does not exist, we say that the sequence is divergent. So another form of divergence is what's so-called divergence to infinity. So for example, if you consider the sequence an, right, which is equal to n, right? So if you write a few terms of this sequence, so 1, 2, so at index 1 you have 1, at index 2 you have 2, you're just plugging the n's here, 3, 4, and so on. So if I tell you what happens as you go far in this sequence, well, you tell me if I reach, for example, 1 million, right? If I reach 1 million, and then I'll have 1,000,001, and so on. So I'll be getting bigger and bigger and bigger. So the sequence is getting bigger with the index. So as n tends to infinity, this sequence is trending to infinity, right? It's getting huge, it's getting big. As the index increases, the sequence is going to infinity. And we might come back to this later to prove this rigorously using the definition of epsilon that we talked about above. But you may take this for granted for now. So if you send n to infinity, right, I mean, intuitively, you're sending n to infinity. So where is this limit going? To infinity, right? This is all we need about divergence for now, and let us go back and prove some of the important limits that we're gonna need in this course. We're gonna use the epsilon definition that we mentioned above only for a few examples, like for the few basic examples that gonna help us build up more like knowledge of limits, right? So this is only needed for these two examples. So if you find this a little bit hard, you can just bear with me to finish these. So the first example that we want to show is that the limit of 1 over n, as we mentioned, the limit of 1 over n as n tends to infinity is actually 0, right? So I remind you, how do you prove that a sequence converges to a limit? So what you do is that you pick any number epsilon positive, and you want to choose n big enough, right, such that if you look at the indices that are bigger than n, you want your sequence to be epsilon close, to be in epsilon distance, like in the sense of absolute value. You want it to be in epsilon distance from the limit L that you're talking about, and this, you need this to happen for every so you need this to happen for every index that is bigger than n, right? So eventually, as n increases, you're asking the sequence to go to L, right? Or to be arbitrarily close to L. So how would we prove that the limit of an, the sequence an equals 1 over n, is 0, right? So we literally mimic these steps. So we start with any epsilon positive. We start with any number that is tiny. You can think of it as a tiny number. And here's what you want. You want that 1 over n, which is the sequence, so this is an, minus 0, the limit, this is the limit, right? You can analogously look here. So this is the limit, L. So you want the sequence minus 0 to be eventually less than the epsilon that we started with. So what does it take? So if you compute this, what is this? This is 1 over n minus 0. This is 1 over n, right? So if you what does it take for 1 over n to be less than epsilon? Well, you want 1 over n to be less than epsilon. So you want, if you do crisscross here, you need n to be bigger than 1 over epsilon. So what indices you can choose so that the sequence is close to that limit? Well, you can choose the indices that are bigger than this this number. So if we choose n to be bigger than 1 over epsilon, then any n that is bigger than that n, right? Any n that's bigger than that n, which is bigger than 1 over epsilon, by construction or by choice, we will have that this inequality, this thing holds. And what this means, we just could prove that the limit of 1 over n as n tends to infinity is equal to 0, right? Which was intuitively clear. So this is the use of the definition. And another thing that we need, so these are just basic examples, we're not going to be needing much, so I think, yeah, so this is the last thing we need. Let me just do this real quick. So the proof that if you take a sequence that is a constant, so for example, if you take the sequence to be 2 always, which means that you're taking the sequence 2, 2, 2, 2, and so on forever, just taking the number 2 forever. So this is a sequence, right? And you're asking, where is this sequence going? Well, intuitively, if all of them are 2, then as we go with big indices, you expect this to go to 2, right? So how would we prove this using the definition of convergence or mathematically? To prove this, we just need, again, we start with any number epsilon positive. That is, you can think of it as a tiny number. You choose n big enough, and you require that an minus the limit that you want to be less than epsilon, as n, like when n is bigger than that n that you chose. So for this case, for example, an is equal to k, right? What is k? Is just a constant. In our case, it can be 2, right? It was 2 in our case. So it's just a constant, it's just a number. An is a fixed number. And you choose an epsilon positive. What n would you choose so we need to make a choice of n such that when you take the sequence, which is an, minus the limit, this is the limit, right? So where are we getting these from? Remember, this is an and this is the limit, right? So you want this sequence minus the limit, and you compute this. What is this? This is 0. So this is always less than epsilon. 0 is always less than epsilon because this is what epsilon is. It's a positive number, right? So you can choose any n that you like. You can choose n equals 1, for example. And then for any n bigger than that n, this will happen, right? It will be that an minus that limit is less than epsilon. So we just proved that if you have a sequence that is a constant sequence, right, and you take a limit of that, let's say the sequence 2, what's the limit of it? It's 2. What's the limit of the sequence as n tends to infinity of the sequence pi? It's just a constant. Well, it's pi, right? So as you see, like these things that you expect are actually true mathematically. So we're now gonna continue, and we're gonna do more examples of limits, but this is gonna be postponed to the next video. We're gonna be presenting some useful properties and facts that's gonna allow you to calculate complicated limits. But the important things that we could prove, for example, are the fact that the limit of a constant is a constant, and the limit of 1 over n is 0. And there's one more important example, which is that the limit of n as n tends to infinity is actually infinity, and so this plus infinity, as n tends to plus infinity is plus infinity, and this can be proved using the epsilon definition, which we might come back to later, but we're gonna now do a little bit of digression here and start studying other properties of limits. But these are mainly the three important examples that's gonna help us build up for other important limits.